Hello everyone. This is the lecture of first part of the second week. We're going to take a look at, as a review, the Mexico earthquake in 1985. As we learned, we have three responses in terms of accelerations, also in terms of velocity, in terms of displacement. For these three responses, we have how many horizontal accelerograms? 2 and 1 vertical accelerograms. The two records for horizontal, east and west, and north and south and up. And we saw that already. And what is important? Three factors. Important of three factors to look at it. These responses. One is a maximum responses. For example, peak ground accelerations. Noticed these 2 points, and positive ups and downs when you move ups and downs here, when you move to the east, when you move to the west, when you move to the south, when you move to the north. Okay. And second thing that we have to be very careful in watching these responses is to look at the natural period or frequencies. Then we can count it per second, how many cycles is going to be completed per second. It's called period. And I'm sorry, this is called the frequencies. And inverse of it is called the period. Okay. And the last one, we're going to take a look at probabilistic durations, how long the earthquake lasts. And these three things that we have to take a look at very carefully when we observe and investigate responses. And okay, this is the same thing that we learned already, so I'm going to skip these slides today. And here, this is a real earthquake from Central 1940, and again, this is a north-south, which is horizontal components. Okay. And peak ground acceleration in terms of G is recorded to 7 something, and similar here. And we have very long duration of the earthquake. A strong duration is about 27 seconds. It's pretty scary when you're under this ground motions. And also we take a look at how many cycles per second, right? So this is difficult to count how many cycles per second. So what I recommend it is to take a look at how many cycles per 10 seconds, okay, per 10 seconds. So we take a look at probably we found 40 cycles per 10 seconds. Then the frequencies, natural frequencies, 4 hertz means 4 cycles per second, right? So if you take a look at into the period, it is a 0.25 second. The official period of a central earthquake is 0.3, so it is close enough, right? So you can just calculate and find the period as what the expert engineers estimate the official period of the earthquake. So this is a very simple but very accurate method to measure frequencies and period. And we do the same thing for next earthquake, which is Mexico earthquake. Okay, this is what we just calculate, 0.25 seconds. And this is another earthquake that we measured from Mexico in 1985. And all we have same information here. And this is a 0.17 plus minus, and this is smaller earthquake but with a different frequency or a different natural period. So we do same thing, and we come up with, okay, this is a 10 cycles per 20 seconds. So the hertz its frequency is 10 to 22 tenth, 0.5 hertz. So 0.5 hertz gives you 2-second period. Right? So this is much longer seismic action, seismic motions compared with that we saw in right here, which is 0.25. What that means is that the ground is much vibrates in horizontal directions faster here than here. It's slower. You make a 1 second. You make a 2 second to make one cycle. 2 second, make one cycle. But here you make a 0.25 second to make one cycle. This is much faster and this is much slower. And these natural frequencies and dominant frequencies, we call it dominant frequencies, and dominant period of the motion will affect your building above, because the building above may get resonance with the vibration that shake its foundations. So, and these dominant frequencies and vibrations is going to be very closely related to understanding how the superstructure sitting on top of this earthquake is vibrating. And what affects these differences? Which factors involves with the dominant period and frequency of the earthquake motions, earthquake ground motions? And we believe one of very important thing that affects these dominant frequencies and period is a soil layer. Okay, we have a soil layer, but soil layers is a few kilometers, but it is really thin skin if you take a look at the whole depth of earthquake. The diameter of the earthquake is 6,400 kilometers. So the few kilometers is not really thick compared to that depth of the diameter. So we call that sometimes not the surface, it's subsurface. Right? Subsurface means we are looking at very thin layer compared with the depth of the earthquake. So many engineers uses this term subsurface conditions forever instead of surface. Okay, so and we have a rocks and very in hard rocks and all that. That'll cause the vibration to be very short, like a 0.2 to 0.5. There is always exceptionals, and also it depends on quality of rocks, but in general, okay, I'm talking the general case, the rock can cause the vibration, seismic vibration very fast. And whereas the sandy clay, soft sandy clay, is going to cause the vibration long period, which is 1.5 to 2 seconds. So this is very long compared to one that you see over there. And this is a similar earthquake that we see at El Centro. Right? El Centro was 0.25. And also this is the similar vibration characteristics that we saw from New Mexico. So this New Mexico earthquake was built on through a soil sedimentary, so that the vibrations getting amplified as it going through the soil, fill the soil or sedimentary soils, so that it really cause earthquake with the big period. And of course, when you have a big, large vibration period, it's gonna cause the superstructure that sits on that earthquake motions. So we're gonna take a look at that later, how the earthquake motions and how the period and frequencies of earthquake motions is related with the dynamic behavior of the superstructures and whether it is okay or not, and will the resonance phenomenon occur or not. It all depends on the dynamic characteristics of the seismic motions. Then we'll take a look at that later. Okay, here we just take a look at how the earthquake motions are looking, and very shortly. Okay, this is not a main part of the course, but it is important for us to understand what type of waves are generated by the earth. Okay, and the earthquake are now classified first of all as a body wave and surface wave. Okay, surface wave, body wave. Body wave occurs and propagates in the body of earthquake, whereas the surface wave is traveling on the surface of the earthquake. That is how we name these two waves, according to where they travel, where they originated, and where they travel. Okay, so body wave also consists of P wave and S wave. Okay, and the surface wave has some names on it: love wave, and some other waves over there. But we don't have to know all the name of the waves. But probably some of you have learned all these waves in high schools and middle schools. And P waves is the waves that vibrates back and forth. This way, your particle vibrates back and forth vertically, axially. And S wave, a particle with S wave is vibrate vertically like this. Okay, this is horizontally, this is vertically. Okay, so that here actually, and this is a short type. So that we call this P wave, which is primary waves, and this S wave is called a shear wave. All right. So this wave, P wave, is faster than S wave, and S wave faster than the love wave and their Rayleigh wave. One more here. Okay. So this surface wave. So when earthquake occurs, you go and see P wave always first. Okay. And let's say this is stations, okay, and this is station at A and B and C and D and E, 1, 2, 3, 4, 5, and the point where the earthquake originated is called a hypercenter, and if you project that on the surface, the point is called a epicenter. Okay, so the origin of earthquake in Earth called hypercenter, and the point on Earth surface is called the epicenter. So we have station over there. So you go P wave propagates, P wave travels, P wave travels, P wave travels, and P wave travels first, and followed by the S wave, shear wave or secondary wave, shear wave or secondary wave. Okay, so this is what you get when you measure at station A, for example. You get a P wave as the oldest possible right there, and then you got S wave follows, and if there is a surface wave, then surface wave follows. P wave, S wave, P wave, S wave, P wave, S wave, surface wave. So that your P waves go this, and you will see the P waves always possible because P waves are the fastest one. And second fastest wave is S wave, shear wave, secondary wave. And you see over there right here. And next you see the surface wave. The surface wave is the slow slowest one, but it is very powerful. So it may cause a lot of damage compared with these two damages. We can take a look at that later.